Welcome to the viewers. This is the fourth lecture in the topic beams and bending. We have discussed how to deal with different types of loads, and also we have discussed problems on simply support beams and cantilevers. And in the last lecture, namely lecture number 133, we have discussed some standard cases of loading, the corresponding bending moment and the shear force diagrams. And since we have discussed load cases combining point load, UDL, UVL, etc. Derivation of these things will be easier. So the viewers are expected to practice all the standard cases because uh, uh, in the second year level, they will ask the derivation. Any problem will be expected to derive. The problem may be even simplest. So you'll have to have enough practice. Now we will take the next case. Now this is lecture number 134, in which we are going to discuss beams with the overhang on both sides. And here the extra thing is we are going to discuss a uniformly varying load plus a couple is applied here, a moment is applied here. How a moment is applied and how we have to deal with the moments also. That's how. And the next information is now this beam is overhang on both sides. Therefore, there will be 2 points of contraflexure. How to locate the points of contraflexure? These are the new information. Otherwise, whatever we have discussed earlier holds good here also. This is to discuss about bending moment and shear force for overhanging beam. Lecture number 134. This is the problem. A problem between the supports, the distance is 12 meters. On the left hand side, you have overhang of 4.5 meters. On the right hand side, you have an overhang of 3.75 meters. The left side, AE, is loaded with uniformly varying load, varying from 0 to 15. Here it varies from 0 to 10. That is about the loading. And here at the center, center of AB, we have a bracket in which a load is applied at a distance of 1 meter, 1 meter from C, 1 meter from C. Now, if this is the case, now, when a load is applied with respect to the axis, when a load is applied at an eccentricity, now here, same diagram is repeated here. Only thing is, we have applied P upward and P downwards, so that there is no change. P and P will get cancelled, you will get this figure, right? This is the case. This can be splitted into the load at the center, this alone, plus these two. These two will cause an anti-clockwise movement. That is what is here. That is P upwards and P downwards will cause an anti-clockwise movement of P into E. So P plus P into E equal to this one. This is equivalent to this, right? So what we have to understand here is when a load is applied at an eccentricity, it will give the effects as that of the same load applied axially plus that of a bending moment. That is what is the point here. When you apply a load here, it is equivalent to applying the same force at the point C plus that of an anti-clockwise moment of 50 into 150 kilonewton meter. This is the result. Right? That. Sometimes they will directly give this moment. Sometimes they will give point load and a moment. That is the important difference that is to be clearly understood. Right now, coming to the analysis, you have to take the moments about B, find out the value of RA, or take moment about A, find out the value of RB. Now here, the moment at A or moment at B will not be 0. However, whatever may be the point, when the moments, the forces to the left and to the right, everything is considered. Algebraic sum of the moments about any point equal to 0. When the forces to the left as well as right are considered, the algebraic sum is always 0. Therefore, we are going to take a moment about the point B. Take a moment about the point B. This calculation will not repeat. Just so about B, it is RA into 12 minus this load into the distance is 12 plus 1/3 of 4.5, and this force 50, and also this moment and this. So this will be causing anti-clockwise moment, and this will be causing a clockwise moment. If that sign and other things are considered, this equation will be simple. We have discussed a number of cases. Let us avoid spending time on this. So calculations are available. You can stop and understand anything at any time, right? RA equal to 65.18 kilonewton meter, and RB equal to total load minus RA. Total load minus RA is 37.32. One is 65.18, the other one is 37.32. So our objective is getting the shear force diagram, bending moment diagram. For getting the bending moment, this is the same beam reproduced, and we will consider x1, x1, x2, x2, x3, x3, and x4, x4. If you are confident, this calculation, detailed calculation is not needed, because we know when it is uniformly varying load, the shear force diagram will have a second degree variation. Therefore, straight away we can take shear force just to the left by adding the total vertical force, or you can do it systematically. If you want to do it systematically, consider a section x1, x1, then Fx equal to minus, left up is positive, this is left down, left sign convention is important, left down, minus the load is half into x into here the ordinate at any section equal to, for 4.5 meters, if it is 15, what is the value for x? So 4.5, 15, for x, what is the value? That is the ordinate. So the area of this is equal to half into x into 15 x by 4.5. That is the shear force. That is the general equation. So it is x square, second degree variation. X equal to 0. When x equal to 0, and the free end E, Fe equal to 0. When x equal to 4.5, Fa equal to minus 33.75. Here, one more point to be remembered here is, now here there is a reaction at this point A. So you have to consider just to the left of the section, so that you need not bother about the value of RA. Just to the right of the section, we have to consider 65.8. So to the left of A and right of A, that is important. So shear force just to the left of A is minus 33.75. Shear force just to the right of A equal to minus 33.75 plus 65.18. So that is equal to 31.43. Because at A, there will be a change in the shear force from negative to positive. You can see the diagram once. Yes, here it is E, it is 0. This is second degree variation. This value is minus 33.75. Then plus RA, when added, you will be getting 31.43. This is the total value is RA. Again, from here to here, there is no loading. It will be constant. Again, there is a concentrator load. Here, there is a concentrator load 50 at C. 50. From A to C, there is no loading. Again, at the point C, you have a vertical load and also an anti-clockwise moment. So you have to consider a section just to the left of C, and just to the right of C. The calculation we have to be little careful. Because in the just to the right of C means this moment will not cause any problem, but the vertical load will be counted. In the bending moment calculation, the axial force will not, the vertical force will not cause any problem, but the moment matters. So that difference you have to note. This is 31.43 will be constant up to the left of C, up to the point where the vertical force and the moment is applied. Up to that point, it will be constant. 31.43 will be constant. Then shear force just to the right of C, right of C. That is, here we have to consider the vertical force. Just to the left of C, it is 31.43. Just to the right of C, it is 31.43 plus minus 50. Downward force minus 50 equal to minus 18.57. So, and again, that will be constant up to the support, right support, up to the right support. Because between C and B, there is no loading. Shear force just to the right of B equal to, here you have to consider the value of RB also. Minus 18.57 is the current value. With this, we have to add this value, upward force, 37.32. So that gives, because we are considering a section just to the right of B. So the reaction is on the left hand side. So left up is positive. Therefore, minus 18.57 plus 37.32 is equal to this value. Coming to shear force to the right of the section, if you are confident this equation is not necessary, straight away you can find out the shear force as total load. Usual procedure considering a section XX at a section X from the right end, this is the equation in which you have to substitute X equal to 0. The shear force at G at the free end is 0. And X equal to 3.75. 3.75 meters is the length of the cantilever, overhanging portion, 3.75. So in X, in the place of X, you substitute X equal to 3.75, you'll be getting this value. This is for the overhanging part. The shear force varies from 0 at the right end G to 18.75 with a second degree variation. So your concept is clear, you can solve any problem, right? So this is second degree. And this is the reaction. We already calculated just to the left of B and just to the right of B. Just to the left of B, it is minus 18.57. Just to the right of B, considering the reaction also, RB also, you get plus 18.75. And in the portion BG, this is the variation, 0 to 18.75. This is the shear force diagram. Since the viewers know all the calculations, let us avoid spending too much of time on this, right? Now coming to bending moment calculations. Bending moment, when it is uniformly varying load, the bending moment will have a cubic variation. Cubic variation, MA is, this is hogging, A to E on the left hand side is hogging and hence negative. So when you write down the equation itself, you have to write with the minus sign. That is very important. Otherwise, when you plot the bending moment diagram, you will have a confusion, plus or minus, etc. Minus half into 4.5 into 15 kilonewton per meter into 1/3 of 4.5. We are taking moment about the point A. Therefore, 1/3 of 4.5 equal to minus 50.625. Uniformly varying load, cubic variation. If you are not confident, then only the second part of the calculation will be needed. That is, if you are confident, you can straight away proceed with this. This is simple and straight. Suppose if you are not confident about the cubic variation, this alternative calculation. That is, consider a section XX, write down the general equation, minus of half into X into this ordinate is 15X by 4.5 into X by 3. This is cubic equation. In this cubic equation, substitute X equal to 0, get the value at the free end, substitute X equal to 4.5 meters, you get this value. So same value, MA minus 50 point something. This is from basics, so that you will be very confident about the cubic variation. But if you are confident, this part of the calculation can be skipped. This is not at all needed. Similarly, x2, 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 x2 equal to that is RA into x minus 4.5. X is measured from the free end. X is measured from free end. This is RA. RA into total is x. This is 4.5. So x minus 4.5. RA 65.18 into x minus 4.5. This is one value. Then minus this loading, half into 4.5 into 15, half into 4.5 into 15 into, from here it will be a 2/3 of 4.5, but you want the distance up to the section x2, so it is x minus 2/3 of 4.5. The distance is x minus 2/3 of 4.5. This is the fundamental equation. So here you substitute, simplify, you find that it has got linear variation. So when x equal to 0, what is the value? X equal to 4.5, because you have taken x from here. We are going to calculate the value at A and the other point C. When x equal to 4.5, you are at the point A. When x equal to 4.5 plus 6, you are at the center. So x equal to 4.5, you find out the value. X equal to 10.5, you find out the value. Again, this is not a must. This calculation you can straight away avoid. Namely, you know the variation means straight away you can take moment. 65.18 into 6 meters up to the point C, minus half into 4.5 into 50 uniformly varying load. The distance to the center of gravity is 6 from C plus 1/3 of 4.5, namely 1.5. This will also give the same value. So this can be straight away used if you are confident about the linear variation concept. So avoiding either first type of calculation, second type of calculation is left to the viewers, right? So bending moment just to the right of C. This is bending moment just to the left of C. We are not considered the moment, because at the point C you got a vertical force and a moment. So here you got a vertical force and a moment. So just to the left of C means we have calculated the bending moment only just to the left of C, right? Just to the right of C means in the bending moment calculations you have to consider the 50. Shear force you have to consider this 50. So here bending moment, there is an anti-clockwise moment that has to be counted here. That is why bending moment just to the left of C and right of C. Just to the right of C is this 137.96 clockwise. This is anti-clockwise, minus 50. So that is equal to 87.96. How to show the variation of these values in the bending moment diagram and the shear force diagram is very important. So considering BG, namely the right side overhanging part, bending moment at B equal to, so bending moment at the point B can be calculated by considering the load to the left of B. That will be tedious, involving number of terms. So compared to that, when you consider the loads to the right, it is easy. Right, you got UDL, say uniformly varying load. So load will be half into 3.75 into 10, triangular loading. Half into 3.75 into 10. When you take moment about the point B into 1/3 of 3.75. It is hugging moment, we know, hugging moment. So calculating MB equal to minus 23.44. Even when you consider all the loads to the left of the section also, you will have the same value that already we have discussed. So this is the bending moment diagram. So bending moment diagram, here it is cubic variation, bending moment. Here also you will have cubic variation. And here, from here to here, you will have linear variation. At this point, there is a moment. So after subtracting that moment, you get the value as 87.96. So this indicates the moment, the anti-clockwise moment of 50 kilonewton, for which you have done the calculation. So this is the calculation, 87.96. So just to the left, it is 137.96. Just to the right, 87.96. Then again, it's only point load, linear variation, and then cubic variation. So we have to calculate the shear force values, bending moment values carefully and plot the variation. Actually, we could have drawn all these diagrams one below the other, but since we are calculating and drawing the diagram I am doing at the end, but what you can do is you can draw the beam below which you draw the shear force diagram, below which you will draw the bending moment diagram. That will be more meaningful. Right. Next is you have to find out the point of contraflexure. There are 2 points. One is in the portion AC. For the portion AC, it is x2, x2. Already we have the equation mx2, x2. Yes, this is the equation. Mx after substituting values, simplification, etc. 31.43x minus 192.06. This is the equation. Now this value is for any point between A and C. A and C, substitute the corresponding value of x and find out the value. But over this distance x, the bending moment changes sign. So mx2 x2 will be equal to 0. That is what we are going to do here, right? This is the definition for point of contraflexure. Already we have discussed in the previous lecture. We need not discuss. We know that if it is one side overhang, you will have 1 point of contraflexure. When both sides there are overhangs, there will be 2 points of contraflexure, 2 points at which bending moment changes sign, right? In the present problem, for the portion AC, mx2 x2 equal to 31.43x minus 192.06. Just now we have seen the equation. At the point of contraflexure, mx2 x2 equal to 0. So 31.43x minus 192.06 equal to 0. That gives x1 equal to 6.11 meter. Now in this case, x is measured from the left free end E. So from the point A, the first point of contraflexure occurs at 6.11 from E minus 4.5. 4.5 is the overhang distance. So say this is x is measured from here x is measured from the point E. So we have calculated x as 6 point something, that is from E up to this it is 6. So we know AE equal to 4.5. If you subtract AE, you will get the distance from A to C, A to the point of contraflexure, that is equal to 1 point something. Right. Now there is another point of contraflexure. Another point of contraflexure is in the portion CB. For CB, we can write down the equation considering all the forces to the left of the section x3. Or it is easier if we consider the forces to the right of the section. So right of the section, we are going to calculate the value of bending moment x3. mx3 equal to 37.32 into x. X is measured from the right end. So x 37.32 into x minus 3.75. When x is measured from the right end, right? So 37.32 into x minus 3.75. Right anticlockwise is positive. Right anticlockwise, we know the sign convention. Then this downward force will cause a clockwise moment about the section x3. Therefore, 37.32 into x minus 3.75 minus half into 3.75 into 10 into x minus 2/3 of 3.75, because the center of gravity of this load will be at 2/3 of 3.75 from the free end, or 1/3 of the distance from the say the point B. The point B. So this equation is given here. First one we have already discussed, x equal to 1.61. In the second portion, for the portion CB, because we know in the portion CB we have one more point of contraflexure. We have one more point of contraflexure here that we are going to find out. So xx mx3 equal to this is the moment due to RB. This is due to the uniformly varying load. So this gives an equation 18.57x minus 93.075 at the point of contraflexure mx3 equal to 0. So this is the equation equated to 0. We will get the value of x equal to 4.964 meters. Again, we have measured x from the end B. So we have to subtract the 3.75. So 4.964 minus 3.75 equal to 1.214. That is, the second point of contraflexure occurs at 1.214 meter to the left of B. So that is how we'll have to find out the point of contraflexure. So that's about the new problem with the double overhanging, combination of uniformly varying load and subjected to a force and a moment at the same. How we have to convert, etc. we have discussed, and that completes this problem. Thank you, viewers. Thank you.